In this video, we're going to develop the inverse of the cosine function, or the arc cosine. And it's going to turn out that the cosine function has all of the same issues that the sine function had. In the previous video, we looked at how to find the inverse of the sine function. So cosine function has the same issues. It is not a one-to-one function. And because it's not one-to-one, it's not invertible. We can tell it's not one-to-one because it doesn't pass the horizontal line test. And like the sine function, if we try to reflect the cosine function in the line y equal x, which is how you get the graph of an inverse function, if we reflect the cosine function in the line y equal x to see what the inverse function looks like, we discover that because the cosine function doesn't pass the horizontal line test, its reflection doesn't pass the vertical line test, and therefore its reflection in the line y equal x is not a function. So the conclusion is that the cosine function does not have an inverse function. So we want to deal with that the same way that we dealt with the issue with the sine function. So let's pause for just a second and write down what we know about the sine function. So we know, the cosine function. So we know that the cosine function plots the x coordinates on the unit circle. So if we have a point xy on the unit circle, the cosine function plots the x coordinates as a function of the angle theta in standard form as we rotate around the function. So the cosine function plots x coordinates, which means it is a function, and it is a function of theta. So it plots the x coordinate that goes with the angle theta as you rotate around the unit circle. So we call it the cosine function, but we shorten it to cos, and we say cos theta. And we know that the vertical axis, the outputs, we're plotting x coordinates, and the horizontal input axis is our angles theta. So we input thetas and we output x's. And we need to do with the cosine function the same thing that we did with the sine function. We need to restrict the domain so that we have a function over a restricted domain that is actually invertible. So what we want to notice is that if we restrict the domain from 0 to pi, the cosine function over that restricted domain will have a graph that looks like this. And that graph will pass the horizontal line test, which means we'll be able to reflect it in the line y equal x and have a function. So if I turn on the restricted domain right there and turn off the cosine over its domain from negative infinity to infinity, if I say, hey, let's just graph the cosine function over a limited domain. So we're going to allow theta. So for the domain, what we'll do to restrict it, we'll allow theta to run from 0 radians to pi radians, or 0 to 180 degrees. And if we do that, we get this nice restricted domain here. When the angle is pi, the output's -1. When the angle is 0, the output is +1. So we see that over this restricted domain, the range of the cosine function will give us x coordinates on the unit circle over the interval from -1 to 1, which is nice because on the unit circle, the x coordinates run from they run from -1 to 1, so that gives us all possible x coordinates. And we want to recognize that our restricted domain, what we're really doing by restricting our domain from 0 to pi, is we're saying, hey, we're going to allow for angles only in quadrants 1 and 2, and we're ignoring every other possible angle that exists. Once we restrict the domain on the cosine function, if we reflect that image in the line y equal x, we get the graph of the inverse cosine function. And there it is right there. And this point will have reflected across the line y equal x over to this point. So what we get is when the input is -1, the output is pi radians, and this point reflects across to here. And we see that that's this point reflected, when the input is 1, the angle was 0 radians. So here's the graph of the inverse cosine function. So what we want to recognize is that the inverse cosine, our inverse function, the outputs are angles, right? The way an inverse works is the inputs become the outputs and the outputs become the inputs. So the outputs will be angles theta. So in inverse notation, if we start to give our outputs a name, we say f inverse of, well, what are the inputs? The inputs are the x values. Or using inverse notation, the cosine inverse of, what are the inputs? The inputs are the x's. Or the other name that we use is arc cosine of, the inputs are x's. The inputs are the x's on the unit circle, and the outputs are the angle theta that generated that x coordinate over the interval from 0 to pi. So because the inputs become outputs and the outputs become inputs, the domain and range of the inverse function are flipped. Its domain is x, an element from -1 to 1. The outputs from the original cosine function become the inputs to the inverse function. And the range then is going to be the restricted domain of the cosine function. So we get angles from 0 to pi radians. If we were in degree world, we'd say from 0 to 180 degrees. So gist of it is, arc cosine is the name of the function. You can use traditional inverse notation. I know that it's common for textbooks to say f inverse of theta or cosine inverse of theta, but I think that's confusing. I like to really identify when we're using this notation that the inputs are x coordinates on the unit circle, the outputs are angles. You can put any x coordinate on the unit circle into the inverse function, but the only angles you're getting out are the angles from 0 to pi.